Okay, in this video, we're going to be looking at solving second-order recurrence relations. That's recurrence relations where the nth term doesn't only depend on the previous term, but also depends on the term before that. We're going to look at one example a bit casually, and then we'll formalize the method. So the first example I want to look at here is un equals un minus 1 plus 6 un minus 2. Note, I'm not going to worry about putting initial conditions in here because that's exactly the same as in first order cases. So our idea, I want to steal an idea we've got from the first order cases. Whenever we're trying to find a complementary function, we normally, in first order cases, have a geometric sequence and we can just say I something times a number to the power of n. So maybe we can try and do a similar thing here, even though this looks like if I gave you initial conditions here, we probably wouldn't get a geometric sequence appearing. But the general solution, maybe we can get a combination of them. So I'd like to know, we've got simpler than we've been doing in first order cases, because in first order cases, we've often had another function added on. This is a homogeneous case here where we've only got the un terms and no extra function included so far. So if we're trying to find a complementary function, as I've said, we'd normally think, oh, well, maybe it's some number times some number to the power of n. So let's try that and let's see what happens. Let's see, well, can we try subbing this in and seeing where we go from there? So I'm going to start by just rearranging this to get equals 0. It's going to make life much easier for us. And if we sub in, we'll get k times lambda to the n, subtract k times lambda to the n minus 1, subtract 6k lambda to the n minus 2. Now, note, if k equals 0 or lambda equals 0, we get a really trivial solution of just all zeros. It's definitely not going to be very general. So we don't really want those to equal 0, so we're free to divide by k, and we're also free to divide by lambda or even lambda to the n minus 2. If we divide by k and lambda to the n minus 2, it's going to become lambda squared, subtract lambda, subtract 6 equals 0. This has suddenly got a lot more friendly, a lot easier to deal with. If we factorize this, lambda subtract 3, lambda plus 2 equals 0, we're getting lambda equals 3, or lambda equals negative 2, and our complementary function here is just going to be some number times 3 to the n. Actually, let me just slow that down. So what is this telling us? This is telling us that k times 3 to the n works as un. It's also telling us that k times negative 2 to the n works. Well, if both those work, then un equals some number times 3 to the n plus some number times negative 2 to the n must also work. And this is going to be our general solution here. Obviously, if I'd given you initial conditions, you could now sub those in and find P and Q, but that's exactly the same as in the first order case. Okay, so let's look at a slightly formalizing this approach before we start to look at non-homogeneous cases. So second example I want to look at, I'm going to tell you that un equals 5 un minus 1, subtract 6 un minus 2. Step 1, rearrange it, get all your un's on one side. So we're going to get just this stuff here equals 0. Because it's equal 0, it's homogeneous, we don't need to go down the trial function route just yet. So from here, what should we do? Well, if we look back at what we did in the previous one, we subbed in and we got k times lambda to the n and so on. But then we divided by the k and we divided by the lambdas and we just got that equation in terms of lambda. I want to skip straight there because that's always going to be the case. We can go straight to saying, once we divide, we're going to have lambda squared, subtract 5 lambda, plus 6 equals 0. This is going to be our auxiliary equation, and we can always just jump straight to that. And now we can go through and we can factorize. Well, if we go through and factorize, then this is telling us that lambda equals 3 or lambda equals 2. So something times 3 to the n would work, something times 2 to the n would work, or more generally, our most general solution, something times 3 to the n plus something else times 2 to the n will work. That's going to be our general solution for a case like this. Okay, time to complicate matters a little bit. Let's look at some initial conditions and having another function involved here as well. So, bigger example going on now. I'm going to tell you the un is equal to 9 un minus 1, subtract 20 un minus 2. So far, similar to the others. But let's say it's plus 24n minus 74. I'll also tell you that u0 is equal to 2, u1 is equal to 15. This is about as hard as we can get. I can complicate that function on our side, but we've dealt with harder child functions before. Okay, so where should we start? Start by just rearranging to get all your UNs on one side. It's always going to be good practice there and just make your life a little bit easier. Okay, so that's the relationship we're trying to solve, this recurrence relation. So 2 steps, same as the first order. Firstly, we're going to try and find our complementary function. That means we're trying to find something that solves this left-hand side is equal to 0. This is exactly what we've just done in those previous examples, and we can jump straight to that auxiliary equation. So un gets replaced with lambda squared, the next term down gets replaced with just lambda, the next term is just a constant, and we're trying to solve that. Factorize, fortunately, I've chosen something nice, that factorize is fine. We have lambda equals 4 or lambda equals 5. And so our complementary function is going to be un equals something times 4 to the n plus something times by 5 to the n. Okay, now we need to do the child function bit, but this is going to be nothing new at all. This is going to be mimicking what we did in our first order cases. We've got a linear function on our side, so we're going to guess the most general linear function possible. Let's make our child function un equals an plus b and just substitute it in to that original equation we had. So we'll be having an plus b, because that was our un. We'll be then be doing subtracting 9 lots of un minus 1, which is going to be all our jazz, plus 20 lots of un minus 2, sorry, that's n, which is going to be this stuff. And we want it equal to, because we were told this earlier, we want it to be equal to 24n subtract 74. At this point, you're just going to expand identical to what you're doing in the first order case. If you do that, you're going to end up with a equals 2, b equals negative 1. So your successful child function is 2n subtract 1. From there, our general solution, again, mimicking what we did in the first order case, is just summing our complementary function, which we got above was p times 4 to the n plus q times 5 to the n, and then added to our child function, 2n subtract 1. And now we're trying to find our particular solution. We need to use the fact that we had u0 was equal to 2, u1 was equal to 15. So if we use those two facts now, we can sub in, get 2 is equal to p plus q subtract 1, 15 is equal to 4p plus 5q plus 1. I've got simultaneous equations we're solving. I'm not going to worry about going through that. P equals 1, Q equals 2, once we've gone through our work. So our final particular solution here then is going to be our general solution with those replaced. We're going to have 1 times 4 to the n, or just 4 to the n, plus 2 times 5 to the n, plus 2n minus 1. Thank you very much.